This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Robert Seacord. Robert Seacord is the Standardization Lead at Woven by Toyota and is the convener of the C Standards Committee. Seacord's previous industry experience includes roles at IBM and the X Consortium. He was a researcher at Carnegie Mellon University Software Engineering Institute, professor at the Carnegie Mellon School of Computer Science and Information Networking Institute, well, that's a mouthful, and the University of Pittsburgh. His previous books include the CERT C Coding Standard, Effective C, which is now in its second edition, and the Secure Coding in C and C++. Robert, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
No, that wasn't bad. The most recent book was the second edition of Effective C, published recently by No Starch Press.
Yeah, it's a good one. I've got that. I've gone through a bit of it for this show, so I'm excited to dig into bits with you.
Cool.
For the listeners, the goals that we're trying to achieve today is to have a short refresher on C, to understand what the C standard, specifically C23, brings, and to explore different sectors where we might find these standards in C in general. So let's start. I'd like to start with a brief history of the C language, what the C standard is, and what the CERT C Coding Standard is. Are you ready?
Sure.
So, when was C created? You should know this instantly.
Oh, yeah, because I was there. I think I was 7, but it was developed in the early 1970s at Bell Labs as a system implementation language for Unix when it was, initially being developed there at Bell Labs.
And what is a standard? What is the C standard? How do they relate?
Yeah, so originally there was no C standard. There was what we called K&RC, which was named after the authors of the C language book back in the 70s, Kernighan and Ritchie. And in the late 70s, folks got together and decided, ANSI in particular, decided it would be useful to standardize the language. The first standard was created by ANSI in 1989, and that's referred to as C89. And then the next year, it was published by ISO as C90. And those two standards are identical. They just have different cover sheets. And there's continued to be standards every decade or so since it's not a quick process. And the standard can kind of be thought of, it's sort of an instructional manual for implementers, but it's also a contract between compiler implementers and users of the language. So the C language is defined by the standard as opposed to, a particular implementation of that standard.
And that's something you can work on. So say you've got the standard in a PDF, you can kind of work and know that as long as you're compliant with it, things are going to work.
Yeah, it's useful to have a copy of the standard. I would say for the entire period of time I was writing operational code in C, I did not own a copy of the standard. And so probably the biggest disadvantage of not having standard is knowing how to write portable code. So, you can sort of experiment with a given compiler and, get your code to work through trial and error and testing, but you don't really know if that code is fully portable unless you're familiar with the standard. So that's probably where the standard provides the most benefit.
And are you aware of any other languages that are standardized like this?
Oh, C++ is standardized like this. Ada, COBOL, Fortran, these are all ISO languages. There are languages like Java and C# where the language itself defines the language. And if you have a sort of difference between the C# standard and the C# compiler, the standard is considered to be wrong. So that's the opposite approach from what C and other ISO languages take.
Before I move us on to the CERT C Coding Standard, are you familiar with what it takes for a language to be one, for there to be desire for it to be standardized? Why isn't there a Java standard, or why isn't there a Golang standard or a Rust standard or something?
Yeah, well, Java was originally developed by Sun Microsystems and sort of controlled by Sun Microsystems. So they wanted to sort of keep control of the language and the process. So they did things like have community groups to provide them input, but they're still roughly under, the control of Sun and then Oracle. C was implemented by different companies at the same time. And what was beginning to happen was there was a certain amount of divergence in the implementations. So the typical reason you standardize something is to sort of limit the divergence and try to have a portable version of the language that you could sort of easily move between different platforms and different compilers.
So you're saying the standardization was done there because of divergence of the language?
Yeah. Different implementations were going in different directions, and there was a desire to sort of try to maintain the portability of code written in the C language, so that you could easily port it from one compiler implementation to another and from one platform to another without too much effort.
And does it make a big difference on the compiler that you use for C?
Well, sure. So to give an example, going into the C standardization process with ANSI and C89, there's this concept called integer promotions in C. And, roughly half the implementations at that time had taken an approach called value preserving, and the other half took this approach of unsigned preserving. So the committee eventually agreed on using the value preserving approach. And then, the roughly half of the compilers who took the other approach then had to change their compilers. And that also has a subsequent impact on the users of the language, right? Because now their compilers change, their version of the language has changed, right? And so they have to now kind of retest all their code and make sure it's still correct given the changes required to standardize.
And when was that example from?
That was from late 1980s.
That makes sense. Okay, so the CERT C Coding Standard.
Yeah, so CERT C Coding Standard was something I worked on at Carnegie Mellon University in the CERT division of the Software Engineering Institute. That actually came about, I had started working in the C Standards Committee in 2005. And about a year later, I went to a meeting in Berlin, and Dr. Thomas Plum approached me. Tom actually just recently passed away, which is sort of sad.
Sorry to hear that.
Yeah, he was a really great man. So he approached me with the idea of CERT creating a secure coding standard. And I thought right away, that's a great idea. And the concern at the time was the only thing out there was from MISRA, which is more of a safety-related standard. And they had their outs with the C committee at the time. And so I started the project back at the SEI, and we published a couple books with Addison Wesley. The first edition was not very good. So if you own that, I'm sorry. But it sort of got me a seat at the table. And we started a study group in WG14, the C Standards Committee. And we met, every couple of weeks for about 3.5 years with security experts and analyzers and compiler vendors. And we kind of ironed out a much better version of the CERT C standard. So we published that in two places. One is the second edition of the CERT C Coding Standard with Addison Wesley, and we also published it as a technical specification with ISO called 17961. And the ISO technical specification was more targeted towards sort of the analyzable subset of the rules, while the CERT C Coding Standard is a little more targeted towards developers and what they needed to do to ensure the security of their systems, even, say, in cases where the enforcement of those rules was not easily tool analyzable.
So if you were to program in C to the C standard, your program might not be secure.
Oh, yeah, it's pretty easy to write an insecure program in C. It's really pretty easy to write an insecure program in any language. There's a lot of things people aren't aware of until they sort of develop a bit of a security mindset. And the start of that is that the user is really actually out to get you in many cases. So whenever you take an untrusted input from a user, / possible attacker, you have to be very careful with those inputs. You have to make sure you validate them. You have to be very careful how you use them, or they might result in some sort of exploit. And that's true of really all languages, all programming languages.
So why is C still so popular if it was created when you were 7 years old?
Well, it's been doing the job. I mean, the kind of advantage of C that makes it attractive is that it's a small, relatively simple language. It's very fast and it just does what you tell it to do. It doesn't do anything else. And so frequently people need that level of control over their programs because they might have to run fast. They might have to be close to the hardware. So, C fits, a niche that is still sort of important today.
Maybe that's like, in software engineering, every 20 years, we kind of reinvent things with the new generation. So maybe with the evolving landscape of languages getting taught at universities and startups and things, it's just not getting so many new projects. I mean, should someone start a new project in C today, or is C just there to be maintained? What's your view on that?
Yeah, I mean, I'm going to give an answer that sounds like a non-answer, but you should start a new project in C if C is the right language for that project. And so there are areas where C is quite, well, I'll say it's sort of best suited still, right? So, for example, if you're developing safety-related systems, it's still a little premature to build those systems in Rust because the ecosystem around Rust is not fully developed yet. So you don't really have the Rust standards that are required for certification. You don't have the certified libraries and a lot of the components that you need to build safety critical software. So, if you have a team of developers and they're C language experts and you have to develop, a safety related system, then C is your best choice. You can't underestimate skill sets and things like that with the developers you have. If you took a bunch of expert C programmers and you asked them to build a system in Rust, chances are good that system won't be as good as the C system would have been just because of the familiarity with the language by the developers.
So are we saying, if I understand that right, pick the right tool for the right job?
Yeah, that's a good summary.
And the niche might be safety-related systems. And what's the definition of safety-related systems? Is that medical, aviation?
Yeah, medical, aviation are both good examples. I work in automotive, so automotive is a good example. So, yeah, there's still a variety of safety-related domains in which C and C++ are the safe choice, right? And Rust would be considered, a really sort of risky, bold choice to make it this time. And eventually Rust will get there, right? But it's not necessarily there quite yet.
Yeah, that surprised me because normally you'd think with a safety standard and all the things you hear about the exploits in C that it wouldn't be used in a safe environment. But because you've got the libraries that are certified and things to reference to create and sign off in medical, I completely understand what you're saying about the immaturity of some ecosystems.
Right. And Rust, has some advantages over C and C++. It's designed to be sort of a memory safe language. The joke is that, programming is hard and, Rust enforces that at compile time. Maybe the joke was programming is impossible and Rust enforces that at compile time. That would have been funnier. So yes, there are advantages of Rust there, but many of the common sort of vulnerabilities are still quite possible. So, no language that I'm aware of enforces input validation, right? That's always left to the programmer. And so, all languages, there are no secure languages, right? They're all susceptible to exploits in one sense or another.
Yeah, I suppose there's a trade-off between developing a safety-related piece of software and the time that takes to do it extra versus some of the quick wins you get in the other languages, that aren't certified, but give you a lot more out of the starting gate, as it were.
Right. Yeah, I mean, C is not a scripting language, right? So you would probably be more likely to use Python or something like that. It's not a web development language. You would be more likely to use JavaScript or TypeScript or something like that. So, languages all have kind of their sweet spot. And, that's still true of C today. There's still various applications, which are really best suited for C. And of course, there's the however many, 50 years of legacy code out there, which basically is what the world runs on, is old C code.
Yeah, exactly. And is there, if somebody asks you where I shouldn't use C, is there something for that, or is there never a wrong place to use C if you know what you're doing?
Yeah, there is. I mean, I've never seen. Well, I guess never is a strong word, right? It's pretty unusual to see C used for a web browser application, right? That's pretty uncommon, and I wouldn't recommend it. And it's probably not the best language for scripting type programs, things that you have to kind of get up and run quickly. So, different languages, again, have their roles, and there are applications that are not well suited to C.
Well, thank you. We're going to move us on to our next section, which is everything new in C. Given it's so old, we're always adding new things with the standards. So, the latest standard, I didn't clarify before, but you called it C89, so I presume that's 1989, and now C23, which is the latest standard, is obviously 2023.
Right. We have our own Y2K problem with the naming of the standards. Like once we get up to 2089, there's going to be some ambiguity in the names. And, given how long COBOL has been around, I wouldn't be surprised if we do get there eventually. One of my grandchildren may be running the C committee by then.
It'll definitely still be around because they're not going to rewrite some of the things that are written in C, are they?
Right.
So now that we've had a good refresher on C, bearing in mind that we last spoke in 2020, 4 years already, what does C23 give us? Or in fact, as we're discussing C23, if there's something that you want our listeners to be highlighted on that's new from C21, so the standard from 2021, if we have any time, feel free to mention that.
Oh, well, there is no C21. So the current version of the C standard is C17. So that's the last published version. C23, we finished work on that in 2023, and it's almost published. So I think we have a commitment from ISO to complete the editing process by December of this year. But it's been a long road with ISO. This has kind of been sort of an ISO issue because it's not just our committees, other committees that are sort of being affected by these long editing schedules.
And that's the ISO International Standard Organization, isn't it?
Right, over there in Geneva.
Yeah. So attributes, you were looking at them in C11, but they didn't get standardized then.
Yeah, we ended up adding some keyword sort of specified attributes. C++, on the other hand, did wind up adopting a standard attribute syntax, but we did get around to them finally in C23. And, it's a useful feature. It's kind of, it's new, so people keep coming up with new things to do with it, right? Because it's got that shiny new car smell.
I think you've mentioned cars. Everyone listening to this podcast in a car or walk or run are going to be going, what is an attribute? So if you want to define it for us, that would be cool.
Yeah. So an attribute is a way to give sort of information to the compiler in a way that if the attribute isn't supported, it's not going to affect the outcome of the program, right? So a lot of times they're just sort of hints to the compiler that it can use for optimization, things like this. So examples of C attributes, which are also present in C++, include maybe unused, no discard, meaning that you shouldn't discard a value returned from a function. And if you do, the compiler should issue a diagnostic. Again, it changes the behavior of the compiler, but doesn't affect the type of code that's generated. There's a deprecated attribute, kind of has a similar effect. There's a no return attribute that you can use to indicate, say, for example, that the function calls abort along all possible control flows. So there's no possible way for that function to return. And as a consequence, the compiler can now sort of make optimizations based on that information.
So is this syntax above a function signature or something like that?
It changes a little bit depending on what it applies to. So the syntactic location of the attribute determines, what it's applying to. So it might apply to, the function, or it might apply to a function parameter, sort of depending on where it's positioned. So you need to look at some examples or look at the grammar in the standard to make sure that you're placing the attributes correctly.
Perfect. So the next item I have on my list is keywords.
Oh, yeah, keywords. So C does something a little bit different than C++, which is we have a reserved namespace of identifiers that we expect the users not to use. And so we're pretty comfortable just clobbering those, right? We'll just take it over for our own use because we reserve them. And the problem is that if a programmer has used that identifier right now, you've got multiple definitions and that could cause problems. So we also sometimes want to use a keyword that's not in the reserved space. And good examples of that are when we added the bool type, when we added static assertions, the static assert macro, a line of, and things like that. So what C does to try to not break user code is a process called uglification. And we really do call it that. So for example, bool, most developers would expect that to be spelled B-O-O-L, sort of like int is spelled bool. But we put an underbar and then we capitalize the first letter. So it was in C17, it's spelled underbar, capital B, lowercase O-O-L. So it's a sort of very ugly version. And that also, the underbar followed by a capital letter is in the reserved identifier space. So if you've used that, we don't feel bad about clobbering it because we'd reserved it. So we had all these kind of ugly keyword spellings in C17, and as part of C23, we replaced those with sort of the modern spelling. So now bool is B-O-O-L and static assert is static assert. And so now you can just use those keywords without having to include any particular headers. And, again, we try to be very careful with C not to break existing code because, as I pointed out earlier, the world runs on C and no one on the committee wants to be responsible for breaking the world. So we try to be quite careful with these things.
And that was Yen, is it Goodstead?
Yeah, Yen Goodstead, I believe, wrote that paper. Yeah, that we
I spoke
voted
to
in.
him, I think, 6 months or a year before I spoke to you in 2020.
Yeah, I think I saw him on your channel. Yeah, he's a very strong contributor to C standards.
That's brilliant. Okay, so the next one, integer constant expression sounds exciting. What was that?
I'm glad you can be excited by integer constant expression.
I'm hoping it spills over.
Not many people can. But yeah, so in C23, we added constexpr, which is familiar to C++ developers. We added it only for object definitions and not yet for function definitions, which, fans of constexpr are immediately disappointed by that we didn't go further. But part of the problem with integer constant expressions is that they're not a portable construct. So vendors are allowed to extend it. So you could declare a function with, say, a const int, and then use that object to provide the size of an array. And on some implementations, that array might be a statically sized array. And on other implementations, it might be a variable length array, a VLA. So this is a good application for these new constexpr objects, where if you declare your size as a constexpr object, now you're portably guaranteed to not have a variable length array. So it improves the portability of your code.
Yeah, because on some platforms, integers could be treated differently.
Yeah, even constant. So constant might be a constant expression on one implementation, but not a constant expression in another implementation, which is confusing, and hence that's sort of where the problem lies.
There's no point thinking of every scenario until it comes across, and then you need to deal with it.
Right.
So the next one, another exciting one for me, enumeration types.
Yeah, I like this change. So most of this change was just the ability to have typed enumerations where the developer explicitly says what type it is. So prior to this change, you sort of had to guess. So it really could be any type up to int or unsigned int. And some common implementations, I believe, for example, Microsoft Visual C used a signed int and GCC used an unsigned int, right? So you got different behaviors on different platforms, and that could, of course, affect portability and how you write your code. And so now, with C23, you can give a type. So you can specify this enum is unsigned short, this enum is an unsigned int, and, now you've got more portable behavior because you know exactly what type is being used to represent the underlying enumeration object.
If you want to use these things now, we've only gone through half of the list. Is it just a case of using a compiler that supports it, or do you need to do something else?
Well, you need a compiler that supports these C23 features, and you need to change your code. So you would have to go through your source code and add the type specification to each enum that you've defined.
And the binary that's produced is just a binary, as how that's always produced.
Yeah, it'll compile down to a binary, and the binary could well be different, right? If you've specified a type for that enum that's different from what the default type would have been under, C17 or older versions. The other thing to be, concerned about is, before you sort of modernize your source code to C23, you want to make sure that those C23 features are available on all the possible, platforms that you're targeting, right? Because otherwise, you wind up doing more work with, having defines and things like that, and different sort of configurations of your program depending on your target compiler.
Yeah, and you end up writing 3 times the amount of code just to do the one thing, depending on where it's deployed.
Exactly. But it is a good feature, and it does improve portability, improves safety and security, because it makes your program better defined, and it's always good to, know what your code is actually doing, right?
Yeah, make it easier to read as well, because you've explicitly said what it is.
Right.
So next one is type and inference.
Yeah, type inference is sort of surprising to me that this became one of the more controversial new features in C. There are a lot of people who really don't want C to change at all, and a few of them are on the committee. So this is, use of auto, and it's the same idea as in C++, but we don't allow it in function signatures. And so what you can do is you can say, auto, I equals 0L, and the compiler will infer the type of the object based on how you initialize it. So in this case, if we initialize it to 0L, the L is the long constant, right? So it will declare this type as a long. So it's sort of a convenient feature. It is sort of susceptible to abuse, which is why maybe some folks are not super fond of it, but it's useful in sort of macro definitions, function-like macros, where you don't know what the type of the parameters are, but you want to declare an object of that type. You could simply use auto there. And it's also useful in generic programming, which, in case you haven't used a new version of C in a long time, we've had for a while now in the language.
Yeah, I was going to ask it because that sounds like in Perl or Python, depending on whether the variable looks like a string or looks like a number or looks like an array, the variable behind the scenes will change.
Right.
So I was just trying to understand what the reason for that was.
Yeah, mostly to support, generic programming, if I had to give a one-line answer.
And what's the short definition of generic programming for those not familiar, including myself?
So 2 sort of generic features. So there's the old school generic feature, which are, function like macros, right? Where say you define a swap function, a swap macro. And, most experienced C programs will know that the actual arguments that you pass to a macro can be any type at all, because it's just going to be sort of textual replacement. And as long as the resulting code makes sense, it will compile and things will be fine. So that's sort of the old school way of doing it. But in C11, we introduce generic selection statement, where now you can actually sort of branch on the type of the parameters and invoke different code. And that code will now be type checked and all those good things that come with not using macros.
Nice. And macros is the syntax you use in pre-processing, isn't it?
Pre-processing, right.
Yeah.
Pre-processing macros. So the # define, basically.
Perfect. Type of operators. That's one word, type of.
Type of, yeah. There's type of and type of unqual. These are similar to the deco type in C++. So it's another way to let you specify a type in your code based on another type or the type of an expression. And so the difference between those two operators, and these are both operators, is that type of retains whatever qualifiers the original type have, like volatile or const or atomic, and type of unqual strips the qualifiers, including any atomic qualifier.
And that might be where you're trying to define a variable to live in one source code file or one program.
Right. It's another useful feature for macros or for generic functions.
Perfect. And second last is bit and byte utilities.
Yeah, this was done by Jean Meneed. So there's a new header called standard bit.h, and there's just a ton of new functions. So we have functions that let you count the number of ones or zeros in a bit pattern, count the number of leading or trailing ones or zeros, test whether a bit is set, determine the smallest number of bits required to represent a value. Just a bunch of different, bit twiddling type of functions that are now standardized. And we also have a feature test macro, standard C endian native, that lets you determine whether your integers are represented using either big or little endian representation.
This area of C and probably software engineering in general, I've not done a lot of personally, any sort of byte operations at all. Where is that used?
Primarily in sort of low-level programming. There's a book, I'm forgetting the name, I think it was called Hacks or something like that. Really very clever book, but it talked about how you can write really efficient code with a variety of sort of these bit-level hacks. So these sort of functions make that easier, but also just for this very kind of low-level code where you're dealing with hardware mass and those type of things.
Yeah, the first thing that comes to my mind is where you're doing embedded programming and you're sending a 1 or 0 to light up an LED or something, different like that.
I just had this thought for the first time, which is always scary to then, record that on a radio show. But this idea that that there's a function to determine the smallest number of bits required to represent a value, that could be quite useful with the new bit precise integer types we have in C23, where you can specify the exact size, the exact number of bits that's going to be used to represent that type.
Well, that's a good idea. So we're on to our last one now. And I'll need to get that link to that book afterwards so we can put it in the show notes.
All right.
So our last one is the IEEE floating point support.
So we have a C floating point study group, and thank God we have them because they handle all this floating point stuff that, befuddles the rest of the committee. But the big change in C23 is that there are a number of technical specifications, 18661, -1, -2, and -3, and those have all been now folded into C23. And so the part 1 of those technical specifications deals with binary floating point. The part 2 deals with decimal floating point, and the part 3 deals with interchange. And so those changes are very extensive and have introduced all sorts of new identifiers, and it's very complete. It also sort of, updates C to work with IEEE 754/2008 version of the floating point standard. So that's good. You kind of do this thing in standards world where you leapfrog each other, right? When we come out with a new standard, we see what other standards have published new editions since the last time we published, and we try to update our standards to work with the latest, greatest things.
How many hours of your life do you have to commit this to know and read off those numbers by heart like you just did, the standards?
Oh, listing them off is pretty easy. Like understanding floating point, that takes your entire life. I mean, there's a really very small number of people who completely understand floating point.
And how do you describe it?
Well, floating point is a model that approximately models the behavior of real numbers, but doesn't really. It's not the same as performing arithmetic with real numbers, but it comes close to it, right? And so that's always good and bad, right? So people will use it to implement arithmetic using real numbers, and normally it works, and then sometimes it doesn't, right? And where and how it doesn't behave the same is why you need to be an expert in floating point when you use floating point.
A floating point, is that like 10.25321? Is that a floating point number or?
Any real number, right? So even like say 0.1 or 1.0, can be a floating point number, right? If it's in a floating point type, such as float or double. And, if I just use 0.1 as an example, right? When you look at that number, in binary floating point, you think that's a really simple number, right? But it turns out in binary floating point, that number cannot be exactly represented. And so there's a certain...
Yeah, but it's 0.1. That's what it is.
That's what you think it is. But when you represent it as a floating point number, it's not exactly that number. It's something close to that number. And so there's a certain lack of imprecision there, which can kind of wind up biting you. It's a weird story to tell. It's a real world example, except it turns out it's not true. It was different, but it's a good story anyway. But back in the 1990s, when we had the Desert Storm, the U.S., invasion of Iraq, there was a Scud missile launch on some barracks in Saudi Arabia. And the barracks would be defended by this Patriot batteries. And it turned out the Patriot batteries had failed to intercept one of these Scud missiles, which hit the barracks and caused some deaths among the U.S. troops there. And so this problem, this defect was originally attributed to floating point representation, and that because these batteries had been continually operational for a long period of time, as it ran, the floating point values became increasingly imprecise to the point that eventually the missiles failed to intercept the Scud missiles coming in. The reality of it is very close to that. The reality is that it was actually an imprecision in these floating point numbers, but it then caused the conversion to an integer to be incorrect. And so, the solution to that was to turn the batteries off and on every so often, so these imprecisions didn't accumulate, and then eventually there was a software fix to solve the problem.
It sounds like the age-old IT fix. Just reboot it.
Yeah, just turn it off and turn it on again.
Yeah. Okay, that's the last one in C23. But have we missed anything?
You probably missed my favorite and maybe many people's favorite, which is starting with C23, the C language only supports 2's complement integer representations. So, as of C17, the C language supports 2's complement, 1's complement, and sign and magnitude. And this is one of these changes, that I didn't think I would live to see.
Yeah, it's a backward step, is that not?
I don't think so, because sign and magnitude representation, that's very, very outdated. 1's complement is one that we thought was kind of still around, but, we determined that really it doesn't exist in any current implementations. And so when you can narrow what's allowed by the standard, that's really the purpose of standardization, right? Now the standard provides more portability guarantees, right? So all you as a developer have to do is write code that will work with a 2's complement representation, and that code will now function correctly on any C23 conforming compiler.
Yeah, that's a big win.
Yeah, I think so.
Perfect.
Yeah, so we did that, and some other things, but too numerous to talk about here.
Well, the last question of this section was to talk about anything in C21 that is a must-have, but C21, as it doesn't exist.
Doesn't exist.
We'll leave that question. That's a new one for me. Okay, so as we said in the intro, you work for Woven by Toyota. So I was wondering if we could talk about that, your work there, how C fits in. Obviously don't talk about things you can't talk about, but what is Woven and what's their goal, as an elevator pitch?
Yeah, so Woven is in the Toyota group of companies. So my office is actually in Tokyo, although I work remotely from my home in Pittsburgh. Woven is basically trying to define what we call the software-defined vehicle. And, so historically, cars have been sort of a collection, built from a collection of components, which are sort of developed by sort of a diverse ecosystem of vendors, and then, integrated by the OEM, which might be Toyota, Ford, or Mercedes, or what have you. And, the software is developed for each component and then basically discarded. And then, for the next version of the vehicle or different vehicle, then, a new set of components are developed. And that's sort of an increasingly unviable way to build cars, which are increasingly software reliant. And so we're trying to sort of flip the script on that and, sort of define the vehicle in terms of the software and then provide the hardware that can then, run that software in a safe, reliable way.
So that was very interesting about Woven. So they're designing, just to summarize, they're designing the software first, so it kind of grows with the vehicle rather than develop software for a component. Then the new version of that vehicle has to get the same process done again and again.
Right. So this is the goal, basically, to be able to sort of preserve the software, evolve it over time, and have sort of increasingly, complex systems that have sort of like reusable software, kind of following the concept of product lines, if you're familiar with that.
Okay, and are they working with other manufacturers to create some type of standard around this as well, or is that too early?
Yeah, it's probably too early. I mean, right now, this concept is competing with sort of the current model, right, where, existing vendors sort of entrenched in the current approach. And, we sort of have to still sort of move the industry in this direction, right? So it's a goal. It's our goal, but it's by no means accomplished the goal yet.
Understood. And where does C fit into all this?
Well, C and C++ are probably the primary languages in which we, develop automotive software, just because, there is this established ecosystem around these languages, and companies like Toyota are very comfortable building or developing automotive software in those languages in C and C++.
Is C kind of powers the operating system, or is that C++, or C just speaks to the individual OEM parts? I've always wanted to know how the systems in a car are linked, and hopefully you are privy to that type of thing.
Yeah, to a degree. They don't really let me write any software anymore, so I am mostly involved in the coding standards and so forth. But, on an embedded processor, you don't really have an operating system, right? You're just kind of on the metal. But there are things like automotive-grade Linux, which might be on a car, and in that case, the operating system is written in C because Linus Torvald can't stand C++. So you won't have it, in Linux. In terms of how the systems, there can be up to, say, 100 ECUs in a modern vehicle. So the vehicle internally has something called a CAN bus, and that's how the ECUs communicate. And the more modern vehicles have sort of more complex networks, which I'm not exactly sure what those look like, but there'll be sort of subnets which are gatewayed off of other networks. So potentially your cyber physical safety components, ECUs, will be gatewayed from the infotainment ECUs, for example.
So you're involved in the standards around all the C code that is used in these safety related systems?
Really all of it. So
okay.
The first coding standards I wrote for Woven were for C++, for C++ 14 and C++ 17. And I'm just actually now completing a C standard around the C17 version of the standard. And these are, coding standards which integrate safety-related coding standards such as MISRA and AutoZAR, and also integrate the CERT standards, which thankfully Toyota had already adopted the CERT standards before I began working there. So I didn't have to sort of do this immodest thing of promoting my own, creations. So that was nice.
And these standards, are they coding standards that the developers follow by reading it, or are they helped with the compilers or the IDEs, or how does it enforce?
So for these MISRA-based standards and AutoZAR-based standards, we have something called a Guideline Enforcement plan, which goes through each of the rules and talks about how it's enforced. And normally it's enforced by some sort of static analysis tool. And so examples of those include CodeQL or Parasoft C++ test or QAC Helix, I think it's called. Those are some examples. LDRA also has a conformance analysis tool. And so, we go through each rule and we point at which checker can, check conformance with that rule. And then in some cases, some of the rules which aren't automatable are enforced through code reviews and other quality assurance processes.
So these are done not at compile time, but through a separate tool, the static analysis. Is that correct?
Right. Yeah. So static analysis is run separately typically after, you can successfully compile the code. And the reason for that is that some of this analysis can take quite a bit of time, and the compilers are really focused on sort of quick turnover, right? Because people have a lot of, edit, compile, test cycles, right? And they don't want to wait very long for their compilations to complete. So yeah, it is typical to sort of break those out into separate tools.
And this would be the trade-off that, for example, Rust made, where they try and do as much as they can up front in the compile bit versus. But that's not safety, though. It's not safety related, but.
Yeah, I'd say that's true. I mean, Rust tries to prevent you from, getting any sort of incorrect code to compile. And the C ecosystem is not necessarily less safe, but it requires that you have a little bit more discipline in that once you get your code to compile, say your code compiles and it has a bunch of warnings, right? It still generates an executable. And if you're a really bad programmer, you might decide to deploy that, right, onto a system. That's poor practice, right? So first of all, compiler warnings are important. You should address all the warnings first, and then you want to do additional analysis, both static analysis, dynamic analysis, testing to make sure that you've eliminated other categories of errors that, you don't want to deploy to your system.
Yeah, exactly. Just a question that's popped out of that last conversation. Have you seen, or is there, or do you ever envisage a way that you could plug in these standards at compile time to see, or for example, Rust, instead of just enforcing what the language do, you can enforce other rules that are safety specific? Or will it always be static analysis because that ecosystem is very mature?
I mean, there's probably no inherent reason why you can't do it. You could quite possibly, Clang has the Clang analyzer, which is a static analysis tool, right? I could envision, Clang introducing a flag that, compile a flag that says also invoke the analyzer. It's not really necessary, right? I mean, it makes more sense to my mind, right, that you do the compilation. And at this point, you're trying to fix warnings. You're trying to get kind of obvious, syntax errors, this kind of thing. So you don't want to spend the time waiting for a complete analysis to finish. You just want, to kind of fix these problems quickly. And then once you get to the point where, it's free from warnings and, it's sort of passing some unit tests, maybe before the unit test, I don't know, then you can do the static analysis and you can look for additional harder to find problems.
Yeah, it might slow down productivity because the warnings are so not related to what you're working on, but you're going to fix them at some point.
Right.
Yeah. Obviously, C is still and always will be a very powerful language, has a strong history and deployment base. And if there is one thing that you'd like our listeners, software engineers, to remember from the show, what would you like it to be, Robert?
C is a strong and flexible language. It's sort of a sharp tool, and you can get a lot done with it, but you need to be informed and, have a good understanding of the language and, program safely.
Perfect. And finally, is there anything that we missed that you think we should have mentioned?
Yeah, run out and get a copy of Effective C 2nd Edition.
Of course. How can I forget? Effective C 2nd Edition.
It makes a great Christmas present for...
I'm looking at my one on the shelf, and it's not too thick, but it's packed with so much information.
Well, thank you very much. Appreciate
That's brilliant. Okay, so people can follow you on X, I suppose, now. Twitter to us, old school.
I'm still on Twitter for the time being and over there on Mastodon and LinkedIn. And I'm not too hard to find. People regularly shoot me emails or, complain about the C language on Twitter, and I'll engage sometimes.
And if there's an acronym that I forgot to write down or put in the show notes and they want to reach out, any of those in particular that you're more fond of or hang around more, or does it matter?
I sort of look at them all. So however you'd like best, whatever system you're on, whatever social media you're on that you'd like to contact me, that's fine.
Okay, Robert, thank you for coming on the show. It's been a real pleasure. And this is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.